vectors acting in the same line or along parallel lines are collinear vectors. This is a set of collinear vectors. This is another set. Parallel vectors have same direction or they are parallel to each other. A set of parallel vectors. Another set of parallel vectors. Anti-parallel vectors have opposite direction. Equal vectors have same direction and magnitude. So if I shift a vector without changing its magnitude and direction, these two vectors are then equal, and we can use this same concept in proving the triangle law of vector addition. Negative of a vector having same magnitude but opposite direction. Here is a vector and another vector which is flipped 180 degrees is the negative of the given vector. Coplanar vectors are the vectors in the same plane. In the diagram we can see there are two vectors in the zy plane which are coplanar vectors. Unit vectors are vectors which have unit magnitude and some direction. The standard unit vectors along the x-axis is I vector or I roof. Similarly, the standard unit vector along the z direction is k roof. Along the y direction is j roof. This is the unit vector along the I direction, j and k. Any arbitrary vector, a vector, can have a unit vector. A roof is equal to a vector divided by its magnitude. If we have a point P, OP is the position vector of this point. Now OP is also equal to xi plus yj plus zk. This is the unit vector notation of OP vector. In a 2D system, a vector A can be represented in polar form, which is A and angle theta, and the unit vector notation is AXI cap plus AYJ cap. In 3D system, we'll have just another component which would be added to the existing X and Y components, that would be AZ K cap. Resolution of a vector along another vector, we have to drop a perpendicular from the given vector to the vector in which we have to find out the resolution of the given vector. We can see two vectors A and B vector. We'll find out the resolution of B vector along A vector. After dropping the perpendicular, this OC vector, this red vector, is basically the component or the resolution of B vector along A vector. In right angle triangle OCB, cos of theta is OC upon OB. So OC is OB cos theta or OC is B cos theta. Similarly, we can find out the component or the resolution of the vector A along B vector, which is A cos theta. A given vector A vector, which has a magnitude of A and angle theta with the positive direction of the x-axis. If we draw perpendiculars from the head A here to x-axis and y-axis, AX is the x component of the vector and AY is the y component of the vector. So A vector can also be written as AX plus AXI plus AYJ. So x component is basically AX, which is equal to A cos of theta. You can also prove it by cos of theta in this triangle OAB. That would be AX by A, or AX equals to A cos of theta. Similarly, the y component is AY, which is equal to A sin theta. Rectangular components of a vector. We have a vector A here, which makes an angle theta with the x-axis. X component is A cos theta and y component is A sin theta. So the A vector is A cos theta I plus A sin theta j. Now if the vector makes an angle theta with the y-axis, then A cos theta would be the y component and A sin theta would be the x component. So the new vector would be A sin theta I plus A cos theta j. Now this will depend on which angle is provided. If this angle is theta, then the y would be A cos theta instead of AX. So don't learn it by heart that always the x component is having cos of theta multiplied with it, because it depends on which angle is specified. If we have another vector which is in the third quadrant, makes an angle theta with the negative direction of the x-axis, then the x component would be minus a cos theta and the y component would be minus a sin theta. So the vector can be written as minus a cos of theta I minus a sin theta j. Let us find components of a vector along two other vectors, other given vectors. Now these two vectors a and c vectors are given vectors, and we have to find the components of vector b along these two vectors. We have to notice that the angle between a and c is not necessarily equal to 90 degrees. So the component of b along a vector is b cos of theta 1 along a roof, which provides that it is along a vector. Similarly, component of b vector along c vector is b cos theta 2 along c roof. Triangle of vector addition states that if two vectors can be represented in magnitude and direction by two sides of a triangle in the same order, as in the head of the a vector would touch the tail of the b vector, then the third side of the triangle taken in the reverse order represents the sum of their magnitude and direction. We are going to prove the triangle law of vector addition now. Given vectors a and b, the b vector makes an angle theta with the a vector. C vector, according to the triangle law, in the which is the third side of the triangle OAB, and taken in the opposite order, is basically the addition of a vector and b vector. This angle alpha is the direction of c vector. Now we have to find out the length of OB, which will be the magnitude of c vector, and the angle alpha it makes with the a vector. In right angle triangle OCB, OB square equals to OC square plus CB square. This is by Pythagoras theorem. Since OC is equal to OA plus AC, therefore OB square equals to OA plus AC, OA plus AC whole squared plus CB squared. In right angle triangle ABC, we can write AC equals to B cos of theta and CB equals to B sin theta. We'll substitute these values in the previous equation and we'll get OB square equals to A plus B cos theta whole square plus B sin theta whole square. So OB, which is the magnitude of C vector, is equal to root over A square plus B square plus twice of AB cosine of theta. In right angle triangle OCB, tan of alpha is BC upon OC. So alpha is tan inverse of B sin theta divided by A plus B cos of theta. This was the proof of triangle law of vector addition. Parallelogram law of vector addition states that if two vectors A and B represent two adjacent sides of a parallelogram, both pointing outwards, then the diagonal drawn through the intersection of the two vectors represent the vector sum of A and B. This is the C vector, which is the vector sum of A and B vectors. The polygon law of vector addition states that if number of vectors represent both in magnitude and direction by the sides of a polygon taken in the same order, then their resultant is represented in magnitude and direction by the closing side of the polygon taken in the opposite order. We can see that here we have a polygon whose sides are represented by A, B, C and D vector. The last side, if we close it in the opposite order, is the R vector, which is the summation of all these four vectors. So R vector is basically equal to A vector plus B vector plus C vector plus D vector.